space looks silent, cold, dark, patient. But that silence is an illusion built by human senses. The universe is not quiet. It is simply speaking in a language most people never learn to hear. High above the atmosphere, beyond clouds and aircraft and cities, the sky produces flashes, not of light, but of radio. Signals so brief they can vanish before the mind even finishes noticing anything happened. A burst lasting only milliseconds. A blink is slow compared to it. A heartbeat is slow. Even a camera shutter feels slow. And here is the unsettling thought. If a signal lasts only a few milliseconds, then whatever produced it cannot be large. It cannot be the size of a star. It cannot be the size of a planet. The source must be compact, tight, violent, and precise. Yet it is powerful enough to cross billions of light years and still arrive at Earth loud enough to be detected. That combination should not exist, and yet it does. The modern story begins in an unglamorous place, an archived recording. In 2007, astronomers searching through older observations from the Parkes radio telescope in Australia found a single, intensely bright pulse. It was short, sharp, and wrong in the best possible way. At first, it looked like interference because radio telescopes live in a world full of human noise. Satellites, radar, communications equipment, and countless devices constantly spill radio signals into the sky. A telescope designed to hear distant galaxies will also hear civilization. But this pulse carried a signature that didn't behave like a local accident. It did not arrive all at once. It arrived smeared across frequency, as if time itself had been combed into strands. Higher frequencies arrived first. Lower frequencies arrived later. That effect is called dispersion, and dispersion happens when radio waves travel through plasma, through clouds of free electrons. The electrons slow different frequencies by different amounts, leaving a measurable delay imprinted onto the burst. That delay was a clue. It suggested the signal had traveled through a long corridor of invisible, ionized material, and the amount of dispersion seemed too large to comfortably explain as a journey through the Milky Way alone. If the burst had truly crossed intergalactic space, then its original emission must have been staggeringly energetic. Distance is cruel. The farther a source is, the more its signal spreads and fades. For a millisecond flash to remain detectable across billions of light years, the event that created it must have been extraordinary. At first, one burst was not enough. Science does not build a theory on a single strange event, especially in radio astronomy, where false alarms are everywhere. Skepticism was not just reasonable, it was necessary. And the universe almost seemed to mock the search, because researchers later discovered bursts that looked similar, but were caused by something embarrassingly local: microwave ovens being opened at the wrong moment near the telescope site. That lesson hardened the field. It forced astronomers to become ruthless about verification. Then more bursts appeared. Different days, different data sets, different telescopes. The sky did it again and again and again. A one-time oddity became a category. A name was born: fast radio bursts, FRBs. And now the mystery sharpened into a paradox. FRBs are not just bright. They are fast. Fast is not a style choice. It is a physical constraint. A burst that lasts 1 millisecond cannot come from a region much larger than the distance light can cross in 1 millisecond, roughly a few hundred kilometers. That is not the scale of a star. It is not even the scale of a planet. It points toward compact objects, the densest engines the universe builds. neutron stars, magnetars, and the extreme environments around black holes. This is why FRBs became irresistible. They look like a snap, a crack, a sudden discharge, something like a cosmic capacitor releasing stored fury. And yet, they travel through intergalactic space and survive. Small source, huge reach. Tiny event, cosmic consequence. But FRBs offered more than a puzzle. They offered a tool. Because dispersion is not just proof that the burst crossed plasma. Dispersion is a measurement. Every FRB carries a record of what it passed through. The free electrons between galaxies leave their fingerprint on the signal. The space between galaxies stops being empty and starts being measurable. In that sense, an FRB is like a lighthouse flash from the far universe. The flash tells you something about the source, but it also reveals the fog between you and it. The universe's invisible matter writes itself into the signal. Even before the origin was understood, FRBs began to hint at something larger. For decades, astronomers have known that ordinary matter does not fully show up where calculations say it should. The numbers suggest it is there, but much of it is hard to see directly. FRBs hint at a way to find it, not by seeing the matter glowing, but by watching how it delays a burst passing through it. A mystery might become an instrument. Then came the twist that shattered many early theories. Some FRBs repeat. Not once, not twice, but many times. At least some sources are not dying in a single explosion. They are surviving, resetting, and firing again. That one fact changes the shape of the entire problem. It suggests engines, not accidents, mechanisms that can recharge, environments that can sustain extreme conditions over time. And it suggests another uncomfortable possibility. Fast radio burst may not be one phenomenon. It may be a family of phenomena that share a similar signature. Different causes, same scream. What we have at this stage of the journey is a set of hard constraints and a growing sense of scale. Fast radio bursts are real. They are extremely short. They can be extraordinarily bright. Many are far beyond the Milky Way. Some repeat, and their signals carry the fingerprints of the invisible material filling the space between galaxies. So the question changes. It is no longer only what produces a burst, it becomes what kind of universe produces so many. Because if our telescopes are catching them by accident, then far more are happening beyond our detection. The night sky is not silent. It may be crowded with millisecond sirens firing constantly across the cosmos. And that forces the next step. To understand FRBs, we must follow the evidence. We must collect patterns, find hosts, measure environments, and watch how these signals behave in different corners of the universe. Because what scientists discovered next would change everything. Once fast radio bursts were confirmed to be real, the mystery stopped being a single, strange signal. It became a pattern hunt, because in science, one event is a rumor. 100 events is a population, and a population has rules. The first rule was already clear. FRBs are fast, which means the engine is compact. But everything else was open. How often do they happen? Where do they come from? Are they all the same kind of event, or are we forcing different things into one label? So astronomers did what they always do when the universe refuses to answer directly. They built bigger ears, they watched more sky, they logged everything. New instruments started catching bursts regularly. Some were classic dishes. Some were wide-field arrays built to scan huge areas of sky at once. And as the detections piled up, the universe began to reveal its habits. One habit was sheer frequency. FRBs weren't rare, not in the cosmic sense. Our telescopes were simply limited. Point at a tiny patch of sky and you might see nothing. Watch a wide patch continuously, and you start realizing the sky is throwing these flashes more often than anyone expected. The implication was unsettling. At any given moment, somewhere in the observable universe, something is firing. Then came the second habit. The signals carried consistent fingerprints of distance. That fingerprint is dispersion. A burst arrives with higher radio frequencies first and lower frequencies later, delayed by free electrons along the path. The larger that delay, the more ionized material the burst passed through. For many FRBs, the dispersion was far too large to be explained by the Milky Way alone. That meant they weren't local fireworks. They were extragalactic. Some were far enough away that the signal began its journey before humans had invented writing. But dispersion wasn't the only signature in the data. There was scattering. Some bursts arrived with a tail, as if the signal had been bounced around by turbulent plasma, smeared slightly in time. There were bursts with multiple peaks, like a single event stuttering. There were bursts whose energy was concentrated into narrow slices of frequency, like a beam threading a needle through the radio band. And then astronomers noticed something especially strange in some repeating sources, a downward drift in frequency from one subburst to the next. The bursts looked like they were sliding, as if the source was playing a note that fell in pitch during the event. It wasn't music, but it had structure. It suggested the engine and its environment were shaping the signal in real time. That's when the field realized something important. FRBs weren't just explosions. They were messages written by physics, and the handwriting could be read. Still, the biggest question remained. Where exactly are these bursts coming from? Because there is a brutal limitation in astronomy. A single radio dish can detect a burst, but it often cannot pinpoint it well enough to identify the host galaxy. It's like hearing a single clap in a city and only knowing it came from somewhere in the north. To solve that, astronomers needed localization. They used interferometers, networks of antennas spread across distances, working together like one giant telescope. With interferometry, the sky becomes sharper. Suddenly, somewhere in the north becomes a precise coordinate. And when the first precise localizations came in, the mystery deepened instead of shrinking. Some FRBs were traced to massive, fairly normal-looking galaxies. Others were traced to small, chaotic dwarf galaxies with intense star formation. The hosts were not uniform. The environments were not uniform. The bursts were not all born in the same neighborhood. This was a major crack in the idea of a single, neat explanation. If FRBs were all the same phenomenon, you might expect them to prefer the same kinds of places, the same galactic habitats, the same stellar populations. But the universe didn't comply. It was telling us, quietly and relentlessly, "You're looking at more than one story." And then came the discovery that forced everyone to rewrite their mental map of the problem. Some FRBs repeat. At first, many theories lean toward cataclysm. A star collapses. A neutron star merges. A one-time catastrophe produces a final radio scream. It's dramatic, it's plausible, and it's clean. Repeaters destroyed clean. Because a repeating source is not a death cry. It is an engine. It can fire again. It can recharge. It can survive. The first famous repeater became a turning point. Bursts were detected from the same patch of sky again and again. The repetition wasn't regular like a clock, but it was undeniable. Whatever this thing was, it wasn't finishing its story in one event. It was continuing. Then localization sharpened the picture further. The repeating source was traced to a specific host galaxy, and the bursts appeared to be linked with a persistent radio glow in the same region. Not every repeater has that kind of persistent emission, but the fact that one did was crucial. It suggested an energetic environment, a place where the engine wasn't alone, but surrounded by something active. A nebula, a wind, a magnetized bubble, a shock-driven region. And the signal itself carried another clue, one so extreme it felt like the universe was underlining the answer with a thick black marker. Polarization. When radio waves are polarized, their electric fields are aligned in particular directions. That polarization can rotate as the signal passes through magnetized plasma. The amount of rotation, called Faraday rotation, reveals how intense the magnetic environment is along the path. Some repeating FRBs showed polarization signatures that implied an environment with extraordinary magnetic fields and dense plasma. Not the gentle magnetism of ordinary space, but something closer to the neighborhood of a highly magnetized compact object. This mattered because it narrowed the list of suspects. An FRB source can't just be energetic. It must be energetic in a way that can create coherent radio emission, shaped by strong magnetic fields, and delivered through a plasma environment that can twist polarization dramatically. This is not the signature of a calm region in a galaxy's outskirts. It's the signature of an extreme engine. But the evidence was still not finished. As more repeaters were discovered, astronomers began to notice patterns. One of the most haunting patterns was periodic activity. A repeating source didn't just fire randomly. It entered an active window on a roughly 16-day cycle. Bursts clustered during part of that cycle, then quieted down, then returned. A cycle suggests a system, not just a star. It suggests geometry, orbit, precession, obscuration, a beam sweeping past Earth, a source that is sometimes visible, sometimes hidden, sometimes aligned just right. And suddenly, the mental picture evolved again. Maybe the engine is a magnetized compact object, but it is embedded in a larger dance, a binary partner, a surrounding wind, a changing environment that gates when we can see the bursts. It was no longer enough to ask, what is the source? Now we had to ask, what is the source doing over time, and who is it doing it with? Then came another wave of evidence that complicated the story even more. Not all FRBs repeat, at least not in the ways we can detect. Some have been observed only once, even after extensive follow-up. And when some of these one-off bursts were localized, they were found in host galaxies that looked different from the first famous repeater's home. Some appeared in more mature galaxies and in locations offset from their galactic centers. That forced a deeper possibility into the room. There may be at least two major classes. Repeaters, likely tied to long-lived engines that can fire many times. And apparent non-repeaters, which might be rare catastrophic events, or simply repeaters with activity too faint or too infrequent for us to catch. Either way, the term FRB began to look less like a single diagnosis and more like a symptom of extreme physics. Now consider what this means. We have signals lasting milliseconds, implying compact engines. We have distances implying enormous energies. We have polarization implying brutal magnetic environments. We have periodicity implying larger systems. We have host galaxies of different types implying multiple formation channels. The evidence isn't pointing toward one neat answer. It's pointing toward a landscape. And in that landscape, the most dangerous mistake is oversimplification. Because the universe does not care how much humans prefer a single elegant explanation. The universe will happily generate the same kind of signal in more than one way, and that is where the mystery becomes truly powerful. Because if FRBs are a family, then understanding them will not only reveal one exotic object, it will reveal multiple pathways by which the cosmos builds extreme engines. And here is the bigger twist. Even without fully understanding the engines, FRBs are already useful. Every burst carries a measurement of the invisible matter it passed through. The space between galaxies leaves its imprint on the signal. The emptiness becomes a map. So as astronomers collect more bursts and tie them to more host galaxies, they are not only learning what creates the flashes, they are also learning what the universe is made of and where that matter is hiding. And that brings us to the next stage of the journey. Because once the evidence pile became large enough, scientists started building frameworks that could connect it all. They began proposing engines, environments, and mechanisms that could explain the diversity without destroying the constraints. And then the universe offered something that felt like the closest thing to a direct confession. A burst from inside our own galaxy. A nearby event that looked like an FRB. A moment when the mystery stopped being only a message from deep space and became something we could study as it happened. What scientists found next would change everything. By now, fast radio bursts stop feeling like isolated fireworks. They start to feel like a system of clues. A millisecond duration tells us the engine is compact. A huge brightness tells us the engine is extreme. Polarization tells us the environment is magnetized. Repetition tells us at least some engines survive. Periodic activity tells us geometry matters. Host galaxies tell us the universe can build these engines in more than one way. So the question becomes sharper and more dangerous. What kind of object can be small enough, violent enough, and structured enough to produce a signal that stays coherent across the void? In radio astronomy, the word coherent matters. Most cosmic radio emission is like a crowd. 1 trillion particles radiate, but not in sync. The result is fuzzy and inefficient. FRBs are different. They behave as if the emission is synchronized, like a choir hitting the same note at the same time. That kind of emission can be astonishingly bright without requiring a star's worth of fuel. But coherence usually comes with a price. It typically demands strong magnetic fields, dense plasma, and an engine capable of organizing chaos into a brief, focused release. That points to a family of objects the universe creates only after something dies. Neutron stars. A neutron star is what remains when a massive star collapses. It packs more mass than the sun into a sphere roughly the size of a city. Matter inside is crushed into an exotic state, and the magnetic field can become unimaginably intense. And among neutron stars, there is a rarer, stranger cousin, a magnetar. A magnetar is not just a neutron star with a strong field. It is a neutron star with a field so strong it dominates the local environment. It can twist plasma, accelerate particles, and store energy in magnetic stress like a loaded spring. When that spring snaps, the star releases a flare. And in some models, that flare drives a shock wave into surrounding material. A shock wave moving through magnetized plasma can act like a natural amplifier, turning a fraction of that energy into a coherent radio flash. This is one of the most compelling frameworks because it naturally explains several facts at once. It explains why the engine can be small. It explains why the environment can be magnetized. It explains why a source can repeat. It explains why the signal can be structured, drifting in frequency, shaped by the plasma it travels through close to the source. It also explains diversity. Not every magnetar lives in the same kind of neighborhood. Some might be newborn, still buried inside a supernova remnant, surrounded by dense magnetized debris. That kind of environment could produce strong dispersion and dramatic polarization effects. Others might be older, wandering in a cleaner region of a galaxy, producing bursts with less environmental distortion. Same kind of engine, different surroundings, different signatures. And if FRBs are a family rather than a single species, magnetars don't have to explain every burst. They simply need to explain a large fraction, especially the repeating ones. But science is never satisfied with a single candidate, no matter how elegant, because there are other frameworks that can also fit parts of the evidence. Some models focus on binary systems. Imagine a compact object orbiting another star or another compact object. The orbit can create periodic activity windows. Bursts might occur only when the engine passes through dense winds, or when a beam is allowed to escape, or when conditions align just right for coherent emission to form. In these models, periodicity is not a mystery. It is a consequence of orbital timing and geometry. Other models focus on the idea of plasma lenses. A plasma lens is like a cosmic magnifying glass made of ionized gas. It can focus radio waves the way a lens focuses light, making a burst appear brighter and more structured. That could explain why some bursts look split into subbursts, or why brightness can vary wildly without requiring the engine itself to change dramatically. In this view, some of the strangeness we attribute to the source might actually be caused by the environment between the source and us, close enough to distort the signal strongly. Then there are models that aim at non-repeaters. If some FRBs truly do not repeat, or repeat so rarely that follow-up never catches them, one possibility is that those bursts come from catastrophic events. Neutron star mergers, collapses, or other terminal processes could release a final coherent burst. That would create a natural two-population picture, long-lived repeaters and one-time catastrophes. But there is a catch. Astronomy has a painful lesson. Absence of evidence is not evidence of absence. A source might repeat, but only once every few years, or only during narrow windows, or only at frequencies we are not monitoring, or only below our sensitivity threshold. So the line between repeaters and non-repeaters might be partly real and partly observational. The real classification may be deeper, different physical channels that sometimes overlap in what we can detect. And that brings us to one of the most important shifts in the entire FRB story. The field stops asking only what produces a burst. It starts asking, how many ways can the universe produce this signature? Because the host galaxies force humility. Some bursts appear in star-forming environments where young magnetars are plausible. Others appear in older environments where a fresh, massive star collapse is less likely. That means at least one channel must produce similar engines long after the era of massive star birth. How do you make a magnetar in an old stellar population? Maybe through rare mergers, maybe through unusual collapses, maybe through binary evolution that builds extreme remnants in ways we are still learning. The point is not that one explanation is right and the others are wrong. The point is that FRBs may be a window into multiple rare pathways of stellar evolution. They are not just fireworks, they are forensic evidence. And now the story becomes even more beautiful. Because even if the engines remain partially hidden, FRBs are already changing cosmology. Every FRB crosses space that looks empty, but is not. It passes through electrons and galaxy halos, through filaments of the cosmic web, through ionized gas that does not shine brightly enough for easy imaging. Those electrons delay the signal. They alter it. They turn space into a measurable substance. This means FRBs are not only objects of study. They are tools. In a very real sense, the bursts are flashbulbs that briefly illuminate the invisible structure of the universe. Each one gives a measure of how much ionized matter lies along the line of sight. With enough localized bursts, you can begin to map where ordinary matter is hiding, in the thin fog between galaxies, in the halos that surround them, and in the filaments connecting the cosmic web like faint veins. And once you can measure that, a huge scientific frustration begins to loosen its grip. For years, astronomers have known that the accounting of ordinary matter did not match perfectly. The universe looked like it was missing a portion of its normal stuff. Not dark matter, not dark energy. Ordinary baryonic matter. Protons and neutrons. FRBs give a way to weigh that missing matter without needing it to glow. They turn the universe into a laboratory where empty becomes measurable. But to turn FRBs into precise tools, one ingredient is essential: localization. You need to know where the burst came from. You need a host galaxy. You need a distance estimate. You need the context that turns a single number into a cosmic measurement. And this requirement has reshaped radio astronomy. A new generation of instruments and pipelines has been built around the idea of catching FRBs rapidly and localizing them almost immediately. Arrays designed not just to detect bursts, but to pin them down to specific galaxies and even specific regions within those galaxies. This is where the story starts accelerating. Because the more bursts we localize, the more the population becomes legible. The more we can separate engine physics from environmental distortion. The more we can tell whether a burst's weirdness comes from the source or from what lies around it. Polarization measurements will also become more decisive. Polarization is not decoration. It is a probe of magnetic structure. It can tell us whether the burst traveled through a strongly magnetized region, whether the field is ordered or tangled, whether the environment is evolving with time. If a repeater's polarization changes across months or years, that hints at a living environment, expanding remnants, shifting winds, changing plasma conditions. And then there is time resolution. The faster we can sample, the more we can see inside a burst. Microstructure on tiny timescales can reveal how emission is produced. It can distinguish between a shock-driven mechanism and a magnetospheric mechanism. It can show whether the signal is made of many tiny shots or a single continuous discharge. As instruments improve, FRBs stop being mere blips. They become detailed events with internal anatomy. Now, consider the future implications if the rate of discovery continues. Thousands of FRBs localized, hundreds of repeaters tracked over years, multiple periodic sources revealing orbital or precessional clocks, population statistics strong enough to link burst types to host galaxy types with confidence. At that point, FRBs become a new branch of observational astronomy, not just a curiosity. And with enough data, the field will be able to answer questions that are currently impossible. How many distinct engine classes exist? Do repeaters cluster in different environments than apparent one-offs? Are there young FRBs and old FRBs in a measurable sense? Is there a continuum or separate species? How much of the observed diversity is physics and how much is propagation through plasma? But the most profound implication is not just about FRBs. It is about how we do cosmology. FRBs can probe matter between galaxies across enormous distances. They can sample lines of sight through the universe that no other method samples in the same way, at the same resolution, with the same frequency. They might help map the cosmic web. They might help measure magnetic fields on intergalactic scales. They might reveal how galaxy halos distribute gas. They might show how the universe's invisible atmosphere evolved over cosmic time. And then we arrive at the edge of the truly mind-bending. Because once you have bursts this short, this bright, and this distant, you can start using them to test physics itself. If the universe has subtle rules that differ from what we think, long-distance signals expose those differences. Tiny delays, tiny distortions, tiny anomalies can become detectable when a burst crosses billions of light-years and arrives with a crisp structure. That does not mean FRBs will rewrite physics tomorrow. It means they give us a new way to ask questions that were previously out of reach. And the history of science has a pattern. New instruments do not merely answer old questions. They create new questions we did not even know how to ask. This is the big picture. FRBs are not only a mystery about an engine. They are a bridge between compact object astrophysics and cosmic scale structure, between violent remnants and the quiet fog between galaxies, between stellar death and the geometry of the universe itself. And now, after building this framework, the story reaches the next threshold. Because the most unsettling part of the FRB mystery is not what we can explain. It is what still refuses to fit, the patterns that feel too sharp, the environments that feel too extreme, the bursts that behave like they are exploiting loopholes in nature's rules. And when we follow those outliers to their logical end, we end up facing questions that are not just scientific. They are philosophical. Questions about what empty space really is, about what the universe allows, and about what it is still hiding inside the static. That is where we go next. By this point, fast radio bursts stop feeling like a single mystery you solve and put away. They start feeling like a doorway, because the more closely you examine them, the more they force you to confront questions that are bigger than any one object. Here is the deepest reason. An FRB is not only a burst of energy, it is also a clock. A burst that lasts milliseconds is already fast by cosmic standards. But when instruments zoom in, some bursts reveal even finer structure, tiny flickers within the flicker, subpulses that appear and vanish so quickly that the event begins to feel less like a continuous flash and more like a rapid sequence of shots. That matters because time is not just a measurement here. Time is a physical constraint. The shorter the burst, the smaller the region that can produce it. Nature is being strict. The universe is saying, if you want to do this in a microsecond, you must do it in a space smaller than most people can comfortably imagine. So whatever the engine is, it is operating at the edge of what matter can survive. Now add the second reality. These signals are coherent. They behave as though countless particles are radiating together in sync rather than randomly. That is how you get extreme brightness without burning through absurd amounts of fuel. But coherence is fragile. It does not happen easily. It needs structure. It needs conditions. It needs an environment where magnetic fields and plasma can organize chaos into a single, sharp release. So FRBs sit at a strange intersection. They are among the fastest, most structured signals the universe produces. They are also among the most distant. That combination turns them into something rare in astronomy, a clean probe. Because a clean probe is not about being simple. It is about being precise. It is about being measurable. A millisecond flash does not give the universe time to hide its fingerprints. Every tiny delay, every twist of polarization, every smear and scatter becomes information. FRBs are not only telling us about their sources, they are telling us about everything between the source and us. Which raises the first ultimate question. What does empty space actually contain? For most of human history, space was imagined as nothingness, a vacuum, a void. But modern astronomy tells a different story. Between galaxies lies a thin, hot, ionized medium, a cosmic haze, so diffuse that it barely shines, yet so vast that it holds a significant fraction of the universe's ordinary matter. FRBs cut through that haze like a flashbulb in fog. The signal gets delayed by free electrons. It can be scattered by turbulence. Its polarization can be rotated by magnetic fields. That means each burst is also a measurement of the universe's invisible atmosphere. This is why FRBs are becoming powerful tools in cosmology. They can help answer where ordinary matter is hiding, how it is distributed, and how it changes across cosmic time. And once you realize that, the mystery becomes two mysteries at once. The engine is one mystery. The medium is another. The burst is a message, but it is also a scan. Now comes the second ultimate question. How many different engines are wearing the same mask? At first, it is tempting to want a single answer. One object, one mechanism, one clean origin story. But the evidence fights that desire. Some FRBs repeat often, some repeat rarely, some appear tied to dense, magnetized environments. Others seem to come from cleaner regions. Some hosts are young and star-forming, others are older. Some bursts show dramatic polarization effects. Others do not. This diversity is not an inconvenience. It is the story. It suggests the universe may have multiple ways to produce a similar radio signature. In the same way that different instruments can hit the same note, different cosmic systems may produce FRB-like flashes through different pathways. That means FRBs are not just a category of object. They may be a category of behavior. A behavior that emerges whenever matter, magnetic fields, and extreme conditions combine in the right way. Now comes the third ultimate question. Can FRBs test the laws of physics across the largest distances imaginable? When a burst travels for billions of years and arrives with a crisp structure, it becomes a natural experiment. If there are subtle effects that accumulate over distance, FRBs are the kind of signal that can reveal them. Consider what an FRB gives you. A sharp arrival time across a wide range of frequencies, a polarization state that can be measured, a source that can be tied to a host galaxy, giving distance, and a path through space that is long enough to amplify tiny discrepancies into measurable differences. This opens the door to testing ideas that usually remain trapped in theory. For example, whether different frequencies of light truly travel at the same speed in vacuum. Whether there are tiny violations of symmetry that only reveal themselves over cosmic distances. Whether magnetic fields in intergalactic space behave the way we think they do. Whether the universe has subtle birefringence, meaning it twists polarization in ways that could hint at new physics. This does not mean FRBs are magical proof machines. It means they are unusually sharp tools, and sharp tools allow you to ask sharper questions. And now we arrive at the most psychologically irresistible question. Could any of this be artificial? People ask it for a reason. FRBs are bright, they are fast, they can look patterned, they can repeat, they can even show cycles of activity. It is the kind of phenomenon that naturally triggers the human instinct to see intention. But the universe is full of things that look intentional when you don't yet know the mechanism. Pulsars were once nicknamed as if they might be signals until physics revealed rotating neutron stars. Nature can produce clocks, beams, and rhythms without any mind behind them. The responsible approach is simple. Keep the question open as a possibility in the abstract, because science never benefits from pretending curiosity is forbidden. But anchor your expectations in what the evidence strongly supports. The strongest evidence points to extreme astrophysical engines, compact objects, magnetic fields, plasma environments, shocks, and geometry. These are not hand-wavy explanations. They are exactly the kinds of ingredients that can produce brief, coherent radio emission. So the most grounded view is not that FRBs are alien messages. It is that FRBs are the universe doing what it does best, building machines out of physics, then letting them run. And those machines are still surprising us. Because even within astrophysics, there are unresolved paradoxes. How does coherence form so efficiently? Why do some repeaters behave like they have seasons of activity? Why do some environments appear so extreme? How do older stellar systems produce FRB engines? What fraction of apparent one-off bursts are truly one-time events? These are not small questions. They are questions about how matter behaves under conditions that cannot be reproduced on Earth. They are questions about the hidden structure of galaxies and the hidden structure of the space between galaxies. In a strange way, FRBs connect the very small and the very large. A compact object the size of a city, a signal that crosses the observable universe. That bridge is the emotional core of the story, because it reminds us that the universe does not require large things to create large consequences. It only requires the right conditions. Now, the final step is to return to the opening idea. At the start of this journey, the night sky looked quiet. It looked empty. Now it looks crowded with events too fast for the eye, too subtle for the senses, but loud enough to be caught by human-built ears. Fast radio bursts are evidence that the universe is not a calm backdrop. It is active, structured, and full of hidden weather. They are also evidence that unknown does not mean unknowable. Every burst carries clues. Every burst constrains theory. Every localized source turns mystery into a map. We are watching a field being born in real time. A few years of detection became catalogs. Catalogs became populations. Populations became patterns. Patterns became tools. And now, tools are becoming a new way to measure the universe's invisible content. So what do we truly know? We know the universe can produce millisecond flashes of coherent radio energy. We know at least some of those flashes come from long-lived engines. We know those engines live in diverse environments. And we know the journey of each signal turns intergalactic space from emptiness into evidence. What we do not know is equally important. We do not yet know how many engines exist behind the label. We do not yet know which mechanisms dominate. We do not yet know the full range of environments these bursts can inhabit. And we do not yet know what surprises will appear when we can localize thousands more. That uncertainty is not a weakness. It is the frontier, because the universe is not obligated to be simple. It is only obligated to be consistent. And consistency is exactly what science is built to uncover. Fast radio bursts are millisecond sirens from the deep cosmos, not warnings, not messages, signals, clues, experiments run by the universe itself. And the most haunting part is this. If our instruments are only now beginning to hear them, then for all of human history, the sky has been flashing in a language we could not understand. Not silent, just unheard. The universe is vast. The mysteries are endless. The journey continues. If you've made it this far, don't just let the universe fade into the background again. Subscribe to Nocturnal Space and keep traveling with us through the dark, one mystery at a time. Drop a comment with the one idea that blew your mind tonight and tell me what you want us to explore next. And turn on notifications so the next signal from the cosmos doesn't pass you by in silence.